So now that we've learned about absolute value functions and quadratic functions, we want to move on to some of the other parent functions and just make sure that we can apply those same ideas, those same characteristics into another context and see the subtle differences in our answers. So the first function we're going to look at is a square root function. And so for us to be able to graph this by hand, we need to come up with a table of x values and y values that we can transform. So when I am plugging numbers into the square root, I'm not going to choose any negative values to plug in. So I'm not going to try -2, I'm not going to try -1, because you can't plug those underneath the square root. I am going to plug in 0 because you can square root 0. And then from there, I'm going to go ahead and pick perfect square numbers so they're easier to take the square root of. So I'm going to do 1 and 4 and 9. So the square root of 0 is 0. Square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. And so when I work with square root functions, the transformations are going to act the same. So this time we're going to say that anything that's underneath the square root is going to be considered inside the function. So the number in the front, that coefficient is still going to tell you if it's reflected or stretched or compressed, all of those vertically. X minus h, that part still tells you if it goes to the left or the right, and it's still kind of the opposite of what you would think. And the number on the end is still going to tell you that it moves up and down. So the point that we move here is not the vertex. It's not called the vertex anymore because if you recall, the vertex is where a graph would switch from decreasing to increasing or vice versa. And that doesn't happen here. So here we're going to have what we call a locator point, and it's still going to come from the exact same spot in the equation. So it's still going to be the opposite of this and then exactly the same as that number there. All right, so let's go ahead and look at this example problem, and we're going to walk ourselves through all of those steps. So the transformations, it is reflected over the x-axis. It has shifted to the left 5 and down 7. The locator point would be -5, -7. And then I'm going to go ahead and get all the information so I can graph this. So I'm going to start with 0, 0, 1, 1, 4, 2, 9, 3. And then I'm going to go ahead and apply those transformations. So the negative in the front means that it's reflected over the x-axis, and so I'm going to change the sign of all of my y-coordinates. It has been shifted to the left 5, so I'm going to subtract 5 from all of my x-coordinates. And down 7, so I'm going to take my y-coordinates and subtract 7. And now I have enough information to graph the function. So if you guys remember, that almost looks good. If you guys remember when we talked about the growth of a quadratic, we said it went over 1 up 1, over 1 up 3, over 1 up 5. So a square root function is actually similar, but it's the inverse. And so we switch what goes up and what goes over. So instead of over 1 up 1, over 1 up 3, we're going to go up 1 over 1, up 1 over 3, up 1 over 5. So up 1 over 1, up 1 over 3, up 1 over 5. This one did the same thing, down 1 over 1, down 1 over 3, down 1 over 5. So it's doing that same pattern that we expected from a quadratic. So for those of you who like to figure out how you could possibly graph these by hand without drawing out the points and making the chart, you're welcome to kind of think through that and see how that would work. The domain of this function, This is going to be the first function we've looked at that does not have a domain from negative infinity to positive infinity. So the domain of this function, we're going to look from left to right. The furthest to the left that the function goes is -5, and we can include that number, so we're going to put a bracket there. And then the furthest to the right that the function goes is an arrow, so that's infinity. The range is going to be a similar process. So we're looking how far down and how far up. So how far down for this one would be an arrow, so that's negative infinity. And then how far up, the biggest y value that we can see is right here at -7. So it's negative infinity to -7. These functions do not have a max or a min. So for max and min, we're going to say none. For increasing and decreasing, a square root function is only going to do one or the other. It is not going to do both. So if I look at this, my stick figure is right here, and he would definitely be decreasing. That's kind of walking down a slope right there. And we have an x value here of -5 and an x value there of infinity. So for increasing, I'm going to say none. For decreasing, I'm going to say from -5 to infinity. Remember, with increasing and decreasing, we always just use parentheses. So I use my parentheses there. This graph is continuous. I can kind of trace it without picking up my finger. So I'm going to say it's continuous. And then for the end behavior, I'm going to say as x goes to the left forever, nothing's happening because this graph stops, right? So as x goes to negative infinity, I'm going to say y is undefined. This graph does not go left forever, it stops suddenly. So we don't have any idea of what it would do on the left side. Well, we do know, we know it stops. As x goes to positive infinity, y is going down, and so we would say y is going to negative infinity. All right, and then just like the other ones we've done, if we want to find the intercepts, we can go ahead and graph this on our calculator. So I've got negative square root, there we go, x plus 5 minus 7. And when you graph it, you can see it's definitely not going to cross the y-axis. It starts down here and it just keeps going. Sorry, it's not going to cross the x-axis because it starts here and keeps going down. So for the x-intercept, we're going to say none. But for the y-intercept, we can plug in 0, and we get -9.236. So x-intercept, none. Y-intercept, -9.236. All right, if we choose points for a cubic graph, we can go ahead and use -2 all the way up to 2, just kind of like normal. So -2 cubed would be -2 times itself 3 times. So -2, -2, -2, and that's -8. -1, -1, -1 would be -1, 0, 1, and 8. We can go ahead and look at what this will be when it's in that transformed form. So again, we have the parentheses right inside, so this is going to feel very similar to what it looks like when you do quadratics. Again, we don't have a vertex because these graphs don't switch from increasing to decreasing. It's like this would increase and then kind of level out right here where that point is in the middle, and then it would keep increasing. So we're going to call this one a locator point, not a vertex. And just like normal, it's at the opposite of this number and then exactly what that number is. So it's kind of similar to what we've been getting used to. All right, so if we look at this problem, let's go ahead and find our transformations so we can make our new chart. So transformations are, it is vertically compressed by 1/2. It has been shifted to the right 1 and up 5. And then I'll go ahead and say the locator point since that's pretty easy to find. 1, 5. So now I can go ahead and write down those points and transform them. So I have that vertical compression of 1/2, so I'm going to multiply the y coordinate by half. And then we're shifting to the right 1, so I'm going to add 1 to the x coordinate. And then we're shifting up 5, so -4 plus 5 is 1, -1/2 plus 5 is +4.5, 0 plus 5 is 5, a +1/2 plus 5 is 5.5, and then 9. So -1, 1, 0, 4.5, 1, 5, 2, 5.5, 3, 9. So if you could see how I drew that, I like to start at the middle, that locator point, and draw like half a parabola going down and then half a parabola going up. That's kind of how you make that little curve. They call these S curves, even though they don't really look like S's, but that's what people call them. Okay, so we have the locator point already. We want to find the domain. The domain and the range for this one is pretty easy because the arrows go left and right and they also go up and down. So there's no x values that skipped and there's no y values that get skipped. And so your domain and your range are both -infinity to +infinity. So that's pretty easy. Again, with this graph, we're not going to have any max or min. So for max min, I'm going to put none. These graphs are interesting because they will either increase for the entire graph or they will decrease for the entire graph. So if I put a little stick figure right here, he's just like increasing, and then it slows down, but it keeps increasing, and then it continues increasing. And a left arrow is a -infinity, and a right arrow is +infinity. So we're going to say that he was increasing from -infinity to +infinity. And for decreasing, we're going to say none. This graph is continuous. If you start tracing it, you can trace the whole thing with your finger. You don't have to pick up your finger to do it. So we're going to say continuous. For the end behavior, we're going to say as x goes to the left, the arrow goes down. So as x goes to the left, the y value is going down. So left, down. As x goes to the right, the y value is going up. So as you go to the right side of the graph, the arrow is pointing up. All right, and then we can go ahead and graph it in our calculators to find those intercepts. So 1/2 x minus 1 to the third plus 5. So I can do second trace, option number 2 to find the zeros of the graph. So my left bound would need to have the cursor a little bit to the left of the point, so it's a little bit underneath. And then I'll go find the right bound. So my x-intercept is -1.154. And then the y-intercept is 4.5. So I'm going to go ahead and leave that. I think the video is getting long enough, and we will do the last parent function at the beginning of class.